All right, so when we had wrapped up class at the end of Wednesday, we had done the output stage of the common base amplifier. We had also looked at the amplifier stage, so we are going to look at the input stage here. Then we're going to do the method of short time constants, and then we're going to call it a day because I haven't cobbled together enough of a lecture for anything else. So let's look up here at what our input stage is effectively going to entail, okay? So we can very obviously see that we have some resistance R sig and a capacitance Cn that are in series. Then we hit node X, looking down, we're going to have a resistance Re, and looking up, we're going to see an input impedance of our common base amplifier where we have some base impedance connected and some collector impedance connected, right? So if we look at our input stage, the ratio of Vx to Vn is just going to be given by a voltage divider relationship where, actually, let me draw this out. So here's our input signal, Vn. Here we see our signal resistance, R sig, in series with some impedance 1 over SCN. Like I said a moment ago, looking down, we see simply the resistance RE. And then looking up, we see an impedance that I'm going to call Zn prime. And then the voltage at node X is just the voltage drop across that resistor Re in parallel with that impedance, Zn prime. So Zn prime from our previous notes is given by R pi plus ZB now, because we have some impedance connected to the base, not just a resistance, times R naught plus ZC. Once again, we're using ZC because we have some total impedance connected to our collector. And then this is going to be divided by R pi plus 1 plus beta R naught plus ZC plus ZB. And as you can imagine, with impedances in both the numerator and the denominator, analyzing this bit directly is going to be an absolute nightmare. So we are going to make the exact same assumption that we did with our common emitter amplifier. So when early effect is neglected, this impedance reduces to R pi plus ZB divided by 1 plus beta, but I'm going to express it as 1 plus GM R pi. And so this is going to be still wildly annoying to use, but not nearly as annoying as the other thing was. So under this assumption, we can say that the transfer function for the input stage is just going to look like RE in parallel with, Zn prime divided by R sig plus 1 over SCN plus RE in parallel with Zn prime. And after several, and I do mean several algebraic steps that I'm not going to make you guys suffer through, this winds up coming out to be S times RE CN times R pi plus R1 in parallel with R2 plus S times R pi times R1 in parallel with R2 times our base capacitance CB divided by a second order polynomial AS squared plus BS plus C, where A is given by R1 in parallel with R2 times R pi times R sig plus RE plus 1 plus GM R pi RE times R sig. And that whole thing right there is multiplied by Cn times Cb. Our polynomial coefficient B is given by R1 in parallel with R2 times R pi plus 1 plus GM R pi times RE, all of that preceding stuff multiplied by CB plus R sig times R pi plus R1 in parallel with R2 plus 1 plus GM R pi times RE, close parentheses there. And then I'm going to sneak some stuff down here because I ran out of room. RE times R pi plus R1 in parallel with R2. Let's see. Close parentheses here. Just making sure all my parentheses are matching correctly. Close bracket, Cn. So just to clarify things here, all this bit right here is multiplied by CB. And then we have R sig multiplied by all this bit right here. And then everything in the square brackets is multiplied by that Cn. I just want to make sure we're all making sure where all of those parentheses and all that kind of stuff are supposed to go. So yeah, it was about 2 hours of straight algebra this morning. It's gross. C is R pi plus R1 in parallel with R2 plus 1 plus GM R pi times RE. So incorporating this information that I have dumped on you effectively, we can see that for our input stage, we are going to have, actually, let me do this as omega z in 1. So we have one pole that is at 0. We have a second pole that's going to be at -1 over actually, no, let's do it this way. It'll be R pi plus R1 in parallel with R2 over R pi times R1 in parallel with R2 times CV. And then our poles are at negative b plus the square root of b squared minus 4ac all over 2a and negative b minus the square root of b squared minus 4ac all over 2a. So that's our direct analysis and rather gross, right? So what we're going to do now is we are going to apply the method of short circuit time constants in order to estimate where our midband begins. Okay. So this is going to be in process exactly the same thing that we did with our common emitter amplifier earlier. We are going to look at each individual capacitor while other capacitors are assumed to be short circuits and determine the resistance connected to our capacitor of interest, right? So if we scroll up here to the very beginning where we look at our circuit diagram, here we go. We've got an input capacitance to worry about. We've got a base capacitance to worry about, and we have an output capacitance to worry about. So let's start by looking at the input capacitance and see what's going to shake out from this thing really quick, right? So when my Vn is grounded, looking to the right of that input capacitance, I'm going to see some resistance R sig. Then on the left-hand side, looking down towards ground, I see RE, and on looking up from the left-hand side of Cn, I'm looking into the source of my transistor. When CV is assumed to be a short circuit, it shorts out R1 and R2, so we're not going to see any base resistance whatsoever, right? And when C out is a short circuit, that's just putting RC directly in parallel with RL. So I believe that the resistance seen looking up is just going to be the resistance looking into the source when we have, like I said, our base is tied to ground, and we replace RC with just RC in parallel with R. So let's look here. So what does Cn see? So I'm going to call this R up. And it's definitely just going to be a resistance because all of those other capacitors are short circuits. Here's RE. Here's where my capacitor is and where I'm looking into. And then here's R sig. So RCN is nothing more than R sig plus RE in parallel with R up. And so what I'm going to do now is I'm going to look through my 335 notes, and I'm going to find out what R up is. So for our common base amplifier with no base resistance, our input resistance, R up, is given by R pi times R naught plus RC over R pi plus 1 plus beta R naught plus RC. And we could approximate this if we were so inclined. So the approximation here is if early effect is neglected, or R naught is much greater than R pi and RC, this just comes out to be approximately R pi in parallel with 1 over GM. So that's what Cn sees. Now let's look and figure out what does CB see. Or so CB is connected between the base node and ground, right? So it is effectively in parallel with resistor R1 and resistor R2 and whatever resistance is seen looking into the base. When we look into the base, we're going to see RC in parallel with RL, and we're effectively going to see RE in parallel with RC in whatever relationship that we have, which actually, so one thing that technically should be here would be RC in parallel with RL, and this should be RC in parallel with RL. I forgot to include that, but we know that it appears in parallel with C out short circuited. Doesn't wind up showing up in the approximation. Actually probably makes our approximation more valid because RC in parallel with RL will always be smaller than what RC originally was, which means R naught's probably more large now. So anyway. All right, so CB is going to see, so if we put our capacitor here effectively, we'd be looking in here and we would have R1 in parallel with R2 in parallel with, I'm going to call it R to the right. So this is the resistance looking into the base terminal of our circuit. So let's sort something out here just really quickly, right? If I drew a small signal model where I'm not worried about R1 and R2 because I understand that that's just going to be in parallel. So I'm looking into my base terminal. So here's my base. Here I would have R pi. This is going to be RE in parallel with R sig, which we could just as easily call RE prime. Here's GM VBE. R naught. And RC in parallel with RL. And we're looking in here to find what I called R right. So we're not going to analyze this because we've seen it before. What does this look like? To me, it looks like the input impedance of a common emitter amplifier with the generator, right? Which we've worked on numerous occasions. So I'm just gonna flip back to my common emitter amplifier notes, find that input resistance, and then make the changes that I need. So here we would see that R right is going to be R pi times RE prime. So that would be RE in parallel with R sig times 1 plus GM R naught times R naught plus RC in parallel with RL times R pi plus RE prime all of this is divided by R naught plus RE prime. So RE in parallel with R sig plus RC in parallel with RL. And in case we didn't want to suffer through literally all of that, assuming R naught is much greater than the other resistance, or assuming the effects of the early effect can be neglected, this looks like R pi plus 1 plus beta RE in parallel with R sig. And now lastly, what does C out see? Let's go back here and see if we can sort things out. So to the right, we obviously see a resistance RL between the right terminal of the capacitor and ground. On the left-hand side, between the capacitor's terminal and ground, looking up, we see RC, and looking down, we see whatever is going to be looking into the collector, where our base resistance is completely canceled out because CB looks like a short circuit. And connected to our emitter, we're going to see RE in parallel with RC again. All right. So here is our capacitor. Here's RL. Let me make sure that that looks like an L for sure. Here's RC. And here is what I'm going to call R down. So the resistance seen by the capacitor C out is just RL plus RC in parallel with what I'm calling R down. R down. So let's see, we would have our base terminal grounded. here at our emitter terminal, we would have RE in parallel with R sig. Here would be GM VBE. And R naught. And this is what we're looking into. As an optional thing here, because you probably actually have this one in the notes that you took in 335, but we definitely have this in the notes that I provided to you for when I reworked this stuff. We could have just put RC right here as well, okay? I'm not going to do that, but I want you to know that that actually is in the notes from 335, and then without that is in the notes from what I provided you guys. So to me, we're looking at the output resistance of a common emitter amplifier, where it's loaded with a current source. If we throw RC away, and it's just got the RC in the place of the current source if we don't throw it away. So I'm just going to the appropriate notes. So current source bias and emitter degeneration are out. So R down looks like R pi in parallel with RE, which is in parallel with R sig, plus R naught, plus GM, excuse me, I wrote the R naught small when it shouldn't have been, times R pi in parallel with RE in parallel with R sig. And with all right, so we were done anyway, so that's a fire alarm. Okay.